So we're going to look at product rule, quotient rule, and chain rule in this video. And we're going to start with some simple cases. And then in the next video, we will kick it up a notch and we will do combinations of these rules. But I want to sort of lay out a way of helping us organize, particularly the product rule and quotient rule, so that it gets easier to figure out when there's multiple things happening at the same time. So we may remember that the product rule, the derivative with respect to x of f times g is equal to f prime g plus g prime f. And so what we need for evaluating our product rule is we need both the derivative of the first function in our product and its original version. And we need the derivative of the second function in our product and its original version. And so what I like to do is I like to make a table. So our f function in this particular case is going to be x squared. That's the first thing in our product. And our g is going to be sine x. And then the nice thing about making the table is that we can then take the derivative of each term separately without having to keep everything in our heads at the same time. So f prime of x is then equal to 2x. And g prime of x is equal to cosine x. And then we recombine them by basically cross multiplying in our table my color pen is too dark here. Oh, there we go. And then cross multiplying this way. So that will combine our f prime with our g and our f with our g prime. Now, because these are added together, it doesn't matter which order we present them in. So y prime is going to be, but I'm going to follow the formula, 2x times cosine x plus x squared. Oh, sorry. 2x times sine x, that's my bad. And then x squared cosine x. So 2x times sine x, x squared times cosine x, and we get our product. Now we can do the same thing for the quotient rule. The quotient rule has similar components, f over g is going to be f prime g minus g prime f all over, that is supposed to be a minus. And then to close the parentheses, g squared. Now, this one does matter in terms of the order that we put the pieces together. And so we do have to pay attention to the fact that the g prime goes after the negative sign, so it has to go second. But aside from that, basically the idea is the same thing. I'm going to make the table. F of x is equal to 2x plus 1, and f prime of x, in this case, is just 2, and g of x is x squared minus 4, and g prime of x It's 2x. And so when we put everything together, y prime. Now in the numerator, again, we can think of this as multiplying these two by these two. In the first term, we're going to have f prime times g. So that's 2 times x squared minus 4. Minus, and then the g prime 2x times 2x plus 1. And then I put a parentheses around the entire numerator because then in the denominator, we need x squared minus 4 squared. So once we have the elements in the table, we can just follow the formula in terms of putting them together. Now, at this point, of course, particularly if you have to go on and do another step, or you have to find the zeros or anything like that, then you would need to do additional algebra in order to simplify this expression. But the focus here that I want is on simply executing the quotient rule. Now, the chain rule, I want to do an example of the chain rule, and then I want to show you how to get around the quotient rule. I, for one, hated the quotient rule because it was another thing I had to memorize when I was taking this as a student. And so once I learned the chain rule, I figured out there was a way of not ever using the quotient rule again and just using the product rule. But first, we have to talk about the chain rule before we can do that. Now, the idea behind the chain rule is that you have a function embedded inside of another function. And the chain idea comes from the fact that you take the derivative of the outside function, you don't change the inside, and then you chain, you stick on the end, the derivative of the inside function. And if, in fact, there's multiple embedded functions, then you keep going. In this example, there's only one embedded function. The sine is the outside function, sine of something. And then the inside function is the x cubed. So one way to think about this is outside is sine of stuff. And then the inside, the stuff, is the x cubed. And so our derivative is going to think of the derivative of the sine part, and we don't change the stuff. And then multiply in the chain by the derivative of the stuff. So there's a portion of it which we don't look inside, we just look at the outside. And then we successively look on the inside, but we don't change the inside on the inside. We only change the inside in the chain portion. So when we take the derivative here, the derivative of sine is cosine, and then we keep the stuff. So the inside portion doesn't change. We only have done the derivative of the sine portion. Sine of something becomes cosine of something. But then, because the something in the middle, the stuff, is not just x, then we multiply by the derivative of the inside. And in that context, then we end up with, if we rearrange this in sort of a more traditional configuration, 3x squared cosine x cubed. And again, the important thing to keep in mind here is that this inside piece does not change until you multiply it on the outside. It does not change inside the function. This doesn't become cosine of 3x squared. it's cosine of x cubed times 3x squared. The thing about the chain rule is that even if you start with a relatively simple looking function like this with one term and no products or anything, your derivative is going to end up looking more complicated. Now that we have the chain rule out of the way, we can look back at our quotient rule problem. And the way that you can get around the quotient rule by using the chain rule and the product rule is to rewrite this function as 2x plus 1 times x squared minus 4 to the negative 1. The negative 1. There we go. Now let's follow through with our product rule. Again, I'm going to build a table. And here, because I'm using the product rule, f of x is 2x plus 1. And the derivative f prime is just 2. Now my g is going to be a little different because I'm using a different formula. G of x is x squared minus 4 to the negative 1. And then g prime, I'm going to use the chain rule to find this derivative. So I bring down my power, negative 1. I rewrite the inside unchanged because I don't look at it until I do the derivative of that part, negative 2, reduce the power, and then I multiply by 2x. And then again, I can cross multiply. Now, with the product rule, it does not matter which order you multiply in. And part of the reason that that works here is because the negative sign is already in the g prime. So the fact that whether you write it first or whether you write it second isn't going to matter. The negative sign is going to go with the term that it needs to go with. So you don't have to worry about, well, like, is it f prime g minus g prime f, or is it g prime f minus f prime g? In the product rule, it doesn't matter. And in the quotient rule, it does. But in the product rule, if you use this method, it also doesn't matter because the negative sign is already with the term that it needs to belong to. So we can go 2 times x squared minus 4 to the negative 1. And then because we're multiplying here, minus, so that's our minus right there, 2x plus 1 times x squared minus 4 to the negative 2 times 2x. Now, if you do the algebra on this to try to make this look like our previous example, then you'll have to do, basically, you'll put the negative powers in the denominator. You'll find a common denominator, which will get you a whole integer power, positive 1 power of this term when you find the common denominator. And then it will look exactly like our previous problem. So these are algebraically equivalent expressions of the same quotient rule. It's just that I achieved this one by doing the product rule instead of the quotient rule. So if you have a hard time losing minus signs, as I tended to do until well into my math career, or if you just don't want to memorize yet another formula, then this will get you around that and it will get you algebraically equivalent expressions. Now, your professor may frown on this because your answer is going to look different than everybody else's answer, but it is algebraically equivalent, and that is the important thing.